Hey everybody, in this video we are introducing energy, kind of a definition, but really focusing on a couple of types, kinetic and potential energy, okay? Now, this is the first time that we've really focused on the word energy, with maybe one or two exceptions. We haven't seen this word in prior videos. We certainly have not defined it, nor looked at types, even though energy is admittedly a word probably many of you are at least familiar with. You've heard of this term. You might even be able to give it a general definition. In terms of physics, it is tough to define energy. It's because there are so many different types of energy, it's hard to have one good definition that really clarifies it. While there is an official definition for energy, especially what we're focusing on, known as mechanical energy, it's not super helpful to us. So to be honest, I recommend you think of energy like this. This is not an official definition, but this is a good way to wrap your head around it. You have energy if you're doing something. That's the main idea. Maybe like imagine any verb that you can think of. If you're dancing, if you're running, if you're thinking, if you're typing, if you're moving, all those things, maybe like a lot of ing type descriptions. Well, that's when you're requiring, or something, it doesn't obviously have to be a person, is using or has energy. Now, something else that is worth mentioning, we've talked about forces before. Forces, it turns out, as a link to energy, forces are required to change an object's energy. If you wanted to give or remove energy from an object, forces are always involved in that process, all right? So that's it. That's kind of our not quite real definition of energy. It's when you're doing something, and it does tie back into forces, something we talked about before in the past. Now, let's see some examples of energy. Some examples of energy are incredibly clear and easy. It's not difficult to imagine at all. A car that is driving down the highway, of course, everybody would say that has energy. A burning candle, that has energy. Maybe you're thinking about the heat, maybe you're thinking about the light. A shining moon or even shining stars, that's doing something. There must be some kind of energy in terms of that. That's probably not too tough to imagine, but I will say, everybody, energy gets a little bit weird. Here I have an example of a really big rock or a really big boulder, all right? Probably none of you would be like worried about this boulder if you're like standing right over here, but also probably a whole lot of you would maybe be a little nervous if you crawled over to this spot. But like this boulder isn't doing anything, so it doesn't have any energy, right? Or how about another example, a battery, not when it's plugged into something, just when a battery is sitting on your desk or sitting in a desk drawer. Does a battery have energy? It's not doing anything if it's just sitting there, but it's a battery, right? We'll get back to that. While it's tough to look at energy as a whole, we can definitely give examples for types of energy. So let's look at our first specific type of energy. It's known as kinetic energy. Moving objects have energy. That's what the word kinetic kind of means. It has to do with motion. It turns out it doesn't matter what you are, whether it's a train or a human being or a planet or an electron, the air blowing in wind, anything that's moving has energy. In fact, the vast majority of different energy types are actually at their core kinetic energy, like the explosion of a bomb. After a bomb goes off and you think of like all the destructive force that bomb has, well, fundamentally, that's the movement of particles like the air, pressure, that's kinetic energy. Or heat, a lot of heat that you feel really has to do with the movement of particles. You actually may have seen that if you're in my own class. Fundamentally, bomb explosions, or at least the destructive power of bombs, as well as heat, most of that is coming actually from kinetic energy. Now, how could you increase or decrease kinetic energy? One way to do that is with speed. More speed, more energy, and that probably makes sense. This person is very lightly tossing a ball. It would have energy, but not a lot. The ball's not moving fast. This individual is pitching. They are throwing the baseball much faster. Everybody would describe this baseball as having more energy because of that higher speed. Similarly, like, you're probably not afraid of someone lightly tossing you a baseball, but man, I would not want to be in the way of this individual after they've thrown a baseball at a really high speed. Why? Because more speed, more energy, all right? Also, everybody, it's not just the speed that determines kinetic energy, but mass also plays a role. Now, I know these two animations are looking like they're showing us two very different speeds, but let's almost pretend they were going the same speed. Even if these two objects were going at the same speed, a few miles an hour, I'm not really worried about a bee like slamming into me going at a couple miles an hour. Even if a train was only moving at a few miles an hour, I would not want to be standing in front of it. Why? Even though they might even go the same speed, a bee has much less mass. It turns out less mass, less kinetic energy. A train, even at the same speed, because it has more mass, it would have more kinetic energy, all right? So kinetic energy has to do with the energy of things that are moving. There's a symbol we use for the energy of moving objects, and that symbol is uppercase letter K. That's nice, K for kinetic. Kinetic energy, as we just saw, is based on an object's mass and velocity, and there is an equation. It's maybe not the toughest equation that we've seen in this class so far, but it's also not the easiest. Kinetic energy is equal to 1/2 multiplied by m, that's mass, multiplied by v, that's velocity, speed, but that speed or that velocity is being squared. Also, everybody, energy, this new kind of topic we have in this video, in this unit for the first time, we haven't seen it before, it has a new unit, a new way to measure that we haven't talked about before. That measurement is joules, or J for energy, all right? Here's that equation, just written again, it's the exact same as before. Kinetic energy is equal to 1/2 mv squared. We measure energy using joules. In fact, we measure all energy in joules. So spoiler, if there's any type of energy we're talking about, it is being measured in our class in joules. Whether it's kinetic or the next type we're about to go over, or any other type of energy, it's measured in joules. Okay, we've done one definition for one specific type of energy. Let's look at one other specific type of energy. That's potential energy, okay? This actually gets back to the examples we were talking about before. Like, this rock arguably isn't doing anything. A battery sitting in the drawer isn't doing anything. A stick of dynamite that's just lying still, it's not lit, it's just in a storage room. Or a landmine, not to get dark, but all these objects, do they have energy? Well, kind of. Like, they have the ability to do something. A dynamite could blow up, a stick of dynamite. A landmine can blow up. A battery could power something. It could give electricity. This rock, if it's not doing anything right now, it has the potential to start sliding down, because here on Earth, gravity pulls things down. So this is one way to categorize energy. If it's not doing something immediately, but it has the ability, if it has the potential, it's almost like it's storing up. It's holding on to energy that it can use later. We call that potential energy. We're going to look at potential energy and actually one subtype of potential energy. All right, so potential energy can be thought of as stored energy that can be used later. An object might have potential energy due to its position. For example, in a battery, there are those two metals and acid. Based on those two materials, based on the fact that there's acid nearby, because of those locations, a battery has the potential to dissolve, give up electrons, etc., etc. A rock up high, because of its position here on Earth, has the potential to do things. The general symbol for potential energy is uppercase U. I don't know why physicists chose uppercase U. Maybe you could research it. I do like to think of it as like, you can do it. You're maybe not doing anything right now, but you have that potential. You can do something later for potential energy. All right, and here's an example I've already kind of said out loud in words. A rock on the edge of a cliff has potential to fall down, but that same rock, if it was on ground level, it wouldn't have that potential. So that's why this idea is actually more important. It has to do with where an object or what a situation is, like where things are located, all right? Just to spell that out more clearly if it's not obvious, this ball right here, maybe it's not yet moving, but because it's up on a hill and planet Earth pulls things down, it would take the slightest of little pushes, and then the ball would of course roll down, go faster and faster and faster. Then it's definitely doing something. It has the potential to do something here, and then later on it's actually then doing something, all right? I actually really like this example, again highlighting this idea of potential. This brick has potential energy. It has the potential to fall straight down, but this brick doesn't have potential. Imagine like you were lying down like on the floor facing up and looking up at this brick. You'd be nervous, of course, because that brick could fall and injure you. It has the potential to be dangerous. But if you were lying on the ground, you wouldn't be afraid of this brick because it's already on the ground. This one can't fall. So again, based on location, based on position, this brick has the ability to do something. It has potential energy. You would say this brick does not have the ability because it's not in the right position. All right, so potential energy. One specific subtype is that gravitational potential energy I was just talking about. It's the energy an object might have because here on Earth there is this force due to gravity. If an object is on Earth and it is at a certain location, a certain position, then it has potential. We call this potential energy, remember, U is used for all potential energy. For this type, the type because of gravity, we label that as UG. These are not two things being multiplied. This is U and a subscript. This is like a particular label, a type of potential energy, gravitational potential energy. It's based on an object's mass. That probably makes sense. It's also based on its height. That should also hopefully make sense based on what we were just talking about. And it is also based on the acceleration due to gravity. How quickly gravity pulls things down, how much it makes them accelerate downward. That would also affect how much energy it has. This is the same lowercase g we've seen before, that 9.8. The equation, UG, that gravitational potential energy, it's equal to m multiplied by g multiplied by h, okay? These are the two equations we just went over. So we introduced energy, a very broad topic, a very broad term that's tough to define. So we focus on two specific types. There's one type based on the force of gravity here on Earth called gravitational potential. That's when an object has a certain height above the ground. There's also kinetic. When something is moving, it has energy. It's based on the object's velocity. They're actually both based on mass. All right, these are energies. All energy is measured in joules. Okay, as always, class, if you're in my own physical classroom, I likely will have some practice where we'll go over these definitions, but that's it. Those are the two types of energies. Thanks a lot for listening. We're going to be building on this idea of energy and the types as we continue. But that's all for this one. Take care.